it's pretty much 4 o'clock, so we'll get started. So I'd like to introduce Camille Perez from the U of A. He's a PhD student, PhD computer science student from the U of A. He's working under the supervision of Martin Jagerson. Yeah, that's right. And he is so robotics and vision labs. That's your.
That's my lab, yeah.
That's his lab.
Yeah, I guess my area would be like robotics and vision, how you combine that to do things. That's the point.
Yeah, so I'll let them take a stand. What's in the box?
Okay, sure. Okay, do you mind if I close the door? Or is it fine?
Yeah, you can go ahead. You don't. Okay. Does it lock?
Okay, no, it was. Okay, so yeah, so my name is Camilo. I'm a student like you from U of A, doing a PhD. I already finished my 3rd year, so I'm gonna try to have here a small summary of what I have done during these 3 years and show you a bit about my research. So let's start with the title. So communication mechanisms for cooperative human-robot manipulation tasks in unstructured environments. It's a really long title, right? Basically, yes, this is the content. Yes, it's important. It's key. So basically, think about today's robots. So with all the technology that we have and everything, why do you think robots are not in our places, like helping us tying our laundry, cleaning our bathrooms, and all the things that we don't want to do? Why do you think that's not happening right now? Do you have any clue, any idea? Residential environment. Yeah, environment is really tough, right? So I want to show you first some video here, small video, short video. So this is an industrial robot, and as you can see, it's pretty fast, pretty accurate. So if a robot can do that, why we cannot put that robot and clean our kitchen, wash our dishes? What do you think? So someone mentioned that it's unstructured, right? So that means that normally in all these setups, like the industrial setups, you have like a control environment where you exactly know where things are going to be, and then you're never going to miss. You can have the precision for moving things really quickly from one place to other without making any mistake, right? That's how this starts. Okay. So these are some robots that you can actually find today. So they're basically toys. I don't know if you're familiar with some of those. Have you seen those before? For sure, yes. So really, basically they're toys, but they already are exhibiting some autonomous behaviors and things like that. But actually, okay, so this is like the toy space, and then like things that will help us doing things in our place will be more like this. So I know maybe you're familiar with iRobot. For sure you know the Roomba and all that stuff. They even have the one that cleans pools and many others. But is that what, when you say robot, is that what you're really thinking? Or is that what you want to have at your place? So maybe you will think or something like that, right? Maybe, have you seen this movie? Maybe Google and try to, it's like a movie. Maybe that's what people will wish to have, but it's still not. I guess we're still a bit far, and I guess these are some examples. Again, these are all in really controlled environments. So here, for example, is Decimo, the Honda robot. Still, this it seems that it's a really natural environment, really human environment, but still this is really controlled. And like, for sure there are like maybe 10 engineers behind this robot at this moment. This is another example. This is from a German university, Karlsruhe. So they actually are doing things like cooking with a robot autonomously. So they have a lot of sensors and they are able to do the thing. But still, it's control, right? So that's a big problem. The other one there is just pictures showing like what I guess what we want, what we all want to have robots just helping us. And here is just a little girl just cooking and showing how easy it is for a human and how hard it is for a robot, right? Yeah. So what's the main challenge there? How we go from there to here? So we have big challenges. We have unstructured environments. And there is another thing that has all these robots, what they have in common. The picture, what you see that they have in common. Any thoughts? So basically, all of them can manipulate things. So that's something that is really powerful. Like humans have evolved a lot and have been able to build on top of other things because we're able to manipulate things and build things. These other robots, the ones that I showed at the beginning, they're cool robots. They can fly, they can move, but actually they cannot build anything. So the ability, the capacity of being able to manipulate things is something that is really hard to achieve in a robot, and a lot of research is done on this field. So these are like big challenges that I guess the researchers are dealing now and working on that. And here is Moravec's paradox. So it is comparatively easy. Maybe here in Kalin sit down, he knows a lot of machine learning, so he can maybe confirm this. It is comparatively easy to make computers exhibit at a level, performance and intelligence tests or playing checkers, and difficult or impossible to give them the skills of a 1-year-old when it comes to perception and mobility. So that's really hard. Like have the ability of coordinate hands with their vision and everything. That's something that is hard to achieve. So we have complex system to control, unstructured environments, and tasks too complex for current artificial intelligence and autonomous control. So what we can do, how we can start working on this problem, at least in a low-level way. So here we go. So how humans achieve tasks. So you have the human have this human body to interact with the environment. And then we have perception, senses, to sense all what is around us, and then we can actually interact, lift things, we can move things from one place to other with really precise movements. But now, what if we do the same thing with a robot? So do you think this is going to work straight away? So we saw before that that's the problem actually. So now what if we, so again the same comment here. So now what if we put the human, so basically what we want is to bring robots closer to human, to help them. So we know for sure that the robot is going to be in a human environment, so humans are going to be, it's not like the factories where everything is controlled and everything is closed, but the advantage of bringing robots to unstructured environments where humans are there, actually there are humans also. So we can take advantage of having humans in the same environment, and that's what we call human in the loop. So basically, what we're going to take advantage of is that actually the human is there, so he can solve problems that the robot cannot solve, and maybe the robot can solve problems that the human cannot solve, and just between that interaction achieve maybe more complex tasks. So the same thing, we have the robot, we have the sensors, the humans still have their senses and he can perceive the world, and then here comes this this part here, right? That is basically what I'm working on. So how do you interact with the robot? So you will say, okay, you can use a gamepad, you can use, but But do you want to be at your place and asking your robot to help you cooking, just give me something or bring me something, and then you want to actually have a gamepad telling your robot to command the robot and then bring, I don't know, the salt or whatever to put, or just a baking powder to put in your cake mix, whatever. You don't want to do that. You want just to actually do that naturally, like what you do with other humans, right? So that's basically what I'm studying, like how you can find natural communication mechanisms that allow you to do this easily. That's I guess my main research. And now what I'm going to try to do is illustrate that with 2 examples. So I guess I did a small talk last time in Elaine's lecture, robotics lecture. I guess I show one of those examples. So is there anyone here from 2 students? Okay. Okay, that's good. So that's going to be a bit of a review for them also. Yeah. So the other thing that you have to notice here is that between these 2, so you can say, okay, the robot can, so you have a big task, and you now have to divide what part of the task is doing the robot, and in which part of the task the human is going to be involved, right? So how you can say which one is the part that the robot should do and which one is the part that the human should be doing. So you can go from really simple data operation systems, but even in the really simple data operation systems, you can try to find better ways of communicating. So I'm going to show you again another video of one showing a simple data operation, but in I guess a different way. So let's start with this one. This is something that we did a demo in the 15th anniversary of the computer science department. So here is actually Martin, he's my supervisor. So what we have here is just so we have this type of and move the robot and do things. So if you see there is another person here controlling the robot and just playing with the balloon from one side to the other side. So this is like a really simple demo, showing just the potential, right? But of course you can do this from remote places. So that's the kind of things that I'm working on. So change the normal gamepad to something that maybe is more natural for the human to interact with. And this one is like okay, so here basically the human was control every part of the robot. And now let's see another one that, so we saw already like the simple data operation. Now we're gonna see another interaction, another type of interaction. I'll show you here. Try to explain you what I'm doing there. So, robot is there. The robot has here a camera. So when we put a camera in the robot, we call this in-hand camera. So I have this visualization. So imagine that we're in. So here I am in the same place, but imagine that you can be like, I can be in an office or someplace, and then I want to operate my robot in my place. I want to do something, right? So again. This is the camera that I'm seeing, and I have a monitor here. I have a Kinect in front of me, who is able to sense where my joints, like he's able to send the position of my joints in my skeleton. So I'm gonna be able to know where is my elbow joint, my hand joint in 3D space. So let's see what's gonna happen. So I do just a simple gesture, and what I did was link my arm directly to the robot arm. So every time I move my arm, the robot arm is going to move. So it has a lot of noise. I guess this video was before I put some filters, but still you can see that you can do coarse motions, and you can still see things here, how it's moving. And I can do another gestures for example, open, close the hand, and do things like that. But then, if I want to get really precise, so here it goes. So we first saw the first video where you have direct operation, but now we have that operation, but we want to add a bit of autonomous, a bit of control. So what I'm doing here is, I stop the robot. Now I'm seeing this screen, and what I'm doing is attaching to my hand a virtual cursor. You will see it soon in the screen. So every time I move my hand, this cursor is moving. So with that, I can actually point in the image what I want, for example, to grasp or to center. What I'm doing here is I'm launching a tracker, an image tracker. So basically what it's going to do is, if you have an image and then you have objects, then you are going to be able to follow that object in the image. There are a lot of methods for doing that, but it's part of the research that we have, just building trackers and use it in smart ways with robots. So what I did there, I actually launched something called a camshift tracker, which is an auto tracker. So I'm just tracking this balloon here, and then with that, I can again go to put the robot in another mode, and then the robot is actually learning how he is moving with respect to the image. And based on that, I can actually do autonomous control of the robot. So here is a simple example where the robot has to end just centering the camera on the target track. You can just do that. We'll just center the camera. And then you can just go back to that operation, and then you can even use another camera, and then you can. So in this example, I was just using one camera. So you're going to be able to just center in the 2D image space. But then if you have a second camera, you can actually get the depth, and you can actually go to the precise location and then send the end effector to that location, and maybe do the grasping of the object. So this is so we saw first the simple dot operation. Now we're seeing the a little more of that operation plus control, and then turn off the robot. But actually what we want to do at some point is maybe something like this. So you have the robot, and then the robot is autonomously taking a cereal box. So you can see how the robot has this robot has almost the same degrees of freedom that we have. But again, this is really control thing. Like, I know how the environment is, so this is not the good thing, right? This is just showing that a robot can knowing the environment, can just go and pick things and just do things. But again, if something changed, it's not going to work, right? Example 2 shows that there is some kind of like if you change things, then if you have you are tracking objects, then you can actually go there, and it's more dynamic. But this one is more like something more like industrial, and maybe that's what we want when we have the intelligence for the robots, but we still don't have that. So now what I'm going to do is show you, I guess, 2 projects where I have been involved, and how I'll be trying to figure out how to connect in this diagram, how to connect this in these examples. So here is the first example. So this is I guess a rehab application. So basically, people have been doing this for a long time ago. So people with upper body disabilities. So they are not able to grasp things. So this is a direct application of using a robot arm to help a person which is disabled. So normally what people have been doing is just they have the wheelchair, they placed a robot arm in one of the sides of the wheelchair, and then they give the person, the disabled, they give them normally a 2D joystick, which they're able to move. They have like small movement, they can do small movements. And with that, I guess the same joystick that they regularly use for wheelchairs, they're using it also for that operate a robot. But you can imagine it's really different, right? You have the wheelchair, and then with the 2D joystick, you can go forward, back, and then you can rotate, and maybe just again go forward and back. But imagine now a robot arm that is 7 degrees of freedom. How you're going to do this with a 2D joystick and map the 7 degrees of freedom just by a 2D plane? It's really hard. So now what you have to do, or what they normally do, is you have modes where you can you move the joystick, and then and maybe we have to stop the video now because I'm going to show the videos off. So that's one of the big problems there. And then, so we have this. We have the robot arm that we want to map with a 2D degrees of freedom joystick. So we want to find, instead of this communication mechanism, what we want to do is something that is more simpler for him to interact with. So what we did, or our proposal, was something really simple. So we have just a vision sensor. So here, I guess, here is the wheelchair. Here is the vision sensor. We have here a small screen, and he can keep his 2D joystick just to interact, or any other device that he used to interact, for example, with a computer or something like that. So this is like the storyboard of what we, at that time, what we were willing to achieve. So imagine that you have a small screen, you have a vision sensor, and then you have objects, and then in the screen, imagine that's the screen, you have all these objects, and then the objects are just detected by the image sensor, and then the user is able to just go on one of the objects, click, and then send the robot there and grasp it and bring it back. That will be the ideal interaction. And then in the case where he has, you notice that, for example, this person has involuntary motions. So in that case, he will not be able to actually go with a cursor and precisely click on the top of the object. So what he's going to be able is just to maybe just shake a bit the joystick and move from one side to the other side. So we can have sort of a discrete jumping between objects. So every time you shake, the system is just going to start jumping between the objects that are detected. And then having that, you're going to be able to select the object. This is another thing that we did. We add like a grasping cursor. So meaning that, and here is where it comes how the human, even a disabled person that is not so capable with his body, but he is really capable with his mind. So imagine that you want to grasp the teddy bear, but then if you're going to grasp it from here, from this side, then you have this obstruction. But then the algorithm doesn't have to solve that because the human has already solved that because he knows that something is there, right? So the human is going to decide, okay, if I cannot grasp her, I'm just going to this side. So that's the way how things are interacting. And yeah, I guess that's basically the storyboard of of what we want to achieve at the time. What we're using for doing that is just depth sensor camera. So I know you're familiar with this, a Kinect. So it's just, it has an RGB camera and a depth sensor. So do you know how it works? Or sort of? So basically, the RGB camera is the color camera that you have regularly, and the depth camera, what it's doing is projecting a pattern, and based on the pattern, it's an infrared pattern, based on the pattern, he's able to find correspondence between the pixels and the depth values, so actually you can get the, per each pixel, you can get the depth value of that pixel. Meaning that if I have, for example, that juggle jar there, I can actually click in that pixel and know how far the jar is from the Kinect. Of course, there are errors there and things that you have to deal with. What you are seeing here is a point cloud visualization, and basically is that. These are like the depth values in a 3D world of all these objects. And then, I guess I'm going to show you a video. Please. So if you have questions or something, just feel free to ask. So I'm going to try to explain what's happening there. So this is actually the visualization of the user. The idea is that he cannot see this, but this is just for illustrating purposes. So we have the main scene, then we have a lot of objects there. The objects are detected. I'm not going to get into the detail of how we detect them unless you want to know that. So you can ask that. But basically what it's doing is detecting all the objects, and then they are marking all the objects there. And this is the scene of the, like what the user is seeing. This is the point cloud visualization. So this is the depth image of that scene, and this is just how the robot should plan to move and to grasp some of the objects. So I'm just going to show you. So basically what I'm doing there is just randomly move the joystick, and that will allow me to just jump between objects. When I get to the object that I want, I just click or do, I guess you can connect that with anything, a button, maybe a blink of an eye, depending on the person, right? And then it shows this discrete cursor with what it's telling you is that you're allowed to grasp from different places. And then you go through that places, and then you just select, okay, I'm just going to try to grasp from top of the object, and then send the robot grasp the thing back. And of course, this is dynamic, meaning that if I move the objects, it's going to be still detecting the objects, and then you can just go and grab. From other place here, for example, I'm just the grasp is from the right side. And again, I'm grasping here from the right side because I know that if I try to grasp from the left side, the robot is going to fly. Unless I have an algorithm that actually allows me to say that there is something there. But actually, I already know because there is. But then it's going to be more complex. Yeah.
So is that completely dependent on the human, or if you select on the left side, is it going to know that there's something in the way and it should grab there?
So I guess it depends. So now what we have is the human is the one who has to do that. But there are algorithms that allow you to do that, right? But then the power that you need, or the processing power that you need, is going to be higher. And you want to really try to shrink the system as small as you want because it's going to be running in a wheelchair. So yeah, that's something that you have to consider. But in principle, it's possible. But then again, you're going to have more things. It's going to be more complex. And again, we go to the same thing. If we have a human that is much more smarter than computer that knows much more about the environment, have better sensors. Why wouldn't use the human where he is really good? He's now bad using physical movements. The robot is good doing that because of the condition of the person. So why wouldn't use his mind and allow the robot to do the physical motion and just so that's the idea. Yeah.
Is there like a panic button to stop it?
Yeah, for sure. Like here I'm using a simple joystick, so this is like more like a lab experiment. But we actually move all this to the jack arm, and that arm has, of course, it has the joystick, the simple joystick. So what you will be doing is you have the joystick to move on the screen and select objects, but at any moment that he wants to stop, he just move really fast the joystick, or just have like a panic button and everything will stop. Yeah, that's something.
Is all the vision operation based on static objects, like if they move, but it?
No, it's not. You can move the objects and, okay, so that's the question. So what I'm doing here, how I'm detecting the objects. So basically, imagine that you have a lot of points with a lot of positions, and you want to know if there are objects or not. So what I'm doing in this particular case is I'm trying to find the closest plane. So I'm building on things that you know that are gonna be there. Like normally things are on top of a table, or are on the wall, or are in different positions that normally you can find it. So a person like that is using one of these types of arms, he's going to need to take things from the, for example, from the fridge and put it in a simple table, or take things from the table. So what I'm doing is detecting the closest plane that is to the robot. After detecting the plane, what I'm doing is see what is on top of the plane. So for finding the plane, there are algorithms for just feed that, so something called ransack. And you can actually feed a model of the plane there. So I find the plane, and then based on the plane, I'll just see what points are on top, and then what I do is just a simple distance cluster. So basically, imagine that all these objects are here, and then I know here is the plane, and then I remove the plane, and all that is here, I know somehow they're going to be objects, right? And then what I do is just cluster this, and then I know, okay, this should be an object, and I can use these points for find the center of the object, build a bounding box, and then start doing more things. So that's the way we're doing this. There are other ways, but this is the way we're solving this here. And yeah, and I guess. Yeah, so I guess this is one of the. So we did experiments testing the interface with a. We just have a. We did experiments with a pilot user. Like we don't have. We couldn't do it with a lot of disabled people, but we tested with like a control group and we'll see how here he just broke the verb. So if he wants to grasp the cup from here, so the robot has to like a really strange movement just to get there. And then what we figured out here was that the more challenging part was just the orientation. So they can operate the robot like for small sections, but then if you have an object here and you start from here, it's going to be hard for him to just get there and get to the right orientation. But to keep that feeling that they are still in control, that the machine is not doing everything. So what we did was, okay, we're gonna allow the robot to do autonomously orientation, meaning that you click and then you say, okay, I'm gonna grasp from right, for example. So the robot just go and just locate the hand here, and we just allow them to go back to the operation and just close this and grasp it, and just press a button to bring it back and break or something like that. Just to keep the loop between the human and the robot. So, yeah, that's okay. So that's what time is it? Have to be faster. Okay, so let's keep that. So here are some, I guess, tests that we did. So we tried this with regular humans also. One test was we just put an object and then we asked the user to use the joystick to calibrate the robot and just put it in the different orientation positions. We take time and then we use our interface and also measure times, how long it takes to do the same thing. So here are like the orientations, and then here are the time it took for each one of the orientations. So we have also, in this data is also the pilot user. So it's yeah, so basically at the end, what we conclude is that, yeah, the interface works, reduced time, but the most important part was that it actually reduced the cognitive load of the person, meaning that when he's doing all these orientations and going to some place and just orient the arm is complicated for the user. Well, if you just make the robot go there and orient it, it's going to feel like more relief, but still we keep the part where he is able to close the loop and actually grasp the thing. So that was good for the, at least for the pilot user that we tested. So with this I finished the first case study. So do you have any questions? Okay. So this was something more applied. It's something that we, like, these type of examples are the ones that we're trying to work on. And I guess we're still working on this and improving the interface, make it better until it becomes a product that actually the company can release and use it with their potential clients. Case study 2. So now we go back to the case where you're a human and then you're at home and then you just want to tell the robot to bring something that is there. So we start with the, I guess, one of the most basic things that we humans do, and is pointing. Just have that, things like that, right? So if you see this image here, can you tell where he's pointing to? Is he pointing to the jug or to the teddy bear or to the possible sphere? Can you tell? The teddy bear, maybe, yeah. Not the teddy bear, okay, yeah. Yeah. So it's really hard to infer. And actually when I'm pointing, if I have this, for example, here, so you will say, no, this is a 2D image, so it's really hard to know, right? Now, so I have these two objects, and I'm gonna, of course, put the teddy bear. There's the teddy bear. So if I have, let's say, this guy here, and this guy here, and if I point there, can you tell me what I'm pointing to? Teddy bear. Do you think? Actually pointing to the jug, but yeah, I guess it's really hard to know that, right? So, again, here it comes again. So maybe we can do something with the robots that are better to do, that are better than humans. So maybe we can do something, make this type of so what they're doing there is just infer where I'm trying to point to, right? So can we do that with the robot? Like actually, can I point and the robot will say, oh, why are you pointing there? I guess that's a possibility. So that's really useful because I guess pointing is one of the things that we, and I guess gestures, but pointing is particularly important because it's not a symbolic gesture. So symbolic gestures are things that change between cultures. But then one thing that is, I would say, universal between different cultures is pointing. Like babies start pointing, I guess, at maybe 8 months and 1.5 years. They start already one that, and that's really something that is in ourselves. So we start by studying how humans point. And this is again the storyboard. So this is how we wish that things happen, that you can just point things and actually you can detect the object that is there, right? So we did experiments. So basically the experiments consist in household situations. So you normally point to things that can be on top of a table, that can be on the floor, or that can be on a wall, right? So that was how we discretized the space. And we test that with different users. And we actually find the accuracy of people pointing to some things and how people interpret how you're pointing. Like with which precision you can tell me that I'm pointing to the teddy bear or to the yogurt container or whatever. And then after having this, we design a system that allows us to do this. So I'm going to try to demo something. Let's see if it works. And so if you have questions, you can start asking. And while I run this, it's going to take maybe 5 minutes. If it works.
I have a question. How important is to use that particular recipient, and what happens if I replace that with this?
So there are different things.
I know you can go ahead and set that up.
Yeah, sure.
So if I replace that recipient that is casted with this one, how much of the software can you choose based on the fact that he knows this is the object? It is what it's looking for, as opposed to this, which is totally unknown. Yeah.
Recording, does it rely on a depth
How does
sensor?
you got a cable?
Do what?
There are all
Does it also
these
use
nice
depth
surfaces
sensor?
and it's just
I'm going to show you now what exactly is happening there.
choose the shape. And that's the point. I mean, you change that to something else, and how do you recommend the shape? You expect a shape like this, right? But then what if it's upside down?
So what I have here
What happens?
is actually what the Kinect is doing now from one of their modes, right? I show you that it has two modes, right? So this is one. This is what we call the point cloud. So this is actually a 3D visualization, so you see. But it's actually more like a shell because it's just what I can see, right? Because of course behind that I cannot complete the model, right? But still is good enough. Let me see this to see a plane, for example, and then to do this type of detection. So yeah, maybe you have, what do you want to put here? Do you have any object?
Yeah, try this.
That one is going to be tricky.
It's
Because
small.
I know, because it's of the...
Oh, it's reflective.
Yeah, exactly. And we'll see. Okay.
Okay, try this.
Actually, it's there. So it's fine. So it's here, right? It's this one here. So it has the center of the object there. And now, okay, so with this, we can see, okay, we have the objects there, but now I want actually to select the object, right? So I keep here with my small demo. Now I'm just going to stand here. Let's see. So I'm someplace here. If you notice, I have now something attached to my hand, like a sphere. And then I have something also attached to my head. It's because of how the visualization is software, but I have something in my head that let me, like a red sphere. So what I'm using there is just these two locations. So if I point to something here, and then I need a mechanism for say that I'm pointing, right? I can use voice, I can use other things. Now what I'm going to do is just use a gesture. So I'm just going to raise my other hand. And you see there is like a red line there that is actually showing where I'm pointing. And actually it appears a red sphere showing where I point, and it shows also a blue sphere showing the position where the robot should grasp the object. Yeah. So in that way, actually, I'm here. I'm like the software is tracking my body, and then I'm able to select different things. So I just select the colleagues copy, and then I'm gonna try to select, for example, something that is more on the other side. So again, array. I select the other thing. Even if I guess if I point there, it will show just the array to some place. This place.
So those two objects that are really close together, select between them like relatively easy.
It depends. So now what the algorithm is doing is just using what he's saying is, okay, I know where is the plane, where there is something on top of the plane, and then what he's doing is just using Euclidean clustering. So basically, this is finding a lot of points and concentrating different regions and just cluster that points. So that's good for, I guess there are a lot of algorithms in machine learning for doing that, right? Just clustering. And then after having that, I build a bounding box on that and say, okay, this is the object. But then if it is really close, what is going to happen is that it's going to be detected like one single object. But then you can use other things on top of the image. So now you're seeing the 3D visualization, but we can also see them. Show you quickly. So now I have also the other image, so it's the 2D image, right? So I can actually point where I'm pointing in the 2D image, so there. And then I can actually run here other algorithms that run just on 2D, like for example the one that I show you, like the camshift tracker, and then use that and combine with that, and that will allow me to separate even more the objects and detect better things, right? Yeah. So I guess the last thing that I want to show you is just so here one of the things that we're solving is actually that we have this problem here, right? You can point, but then you're going to have an error between objects, right? So one of the things that we're doing is when we point, we are also correcting what we think the user is where he's pointing. But again, when I point there and you said the teddy bear, but probably I was pointing to the junkyard, right? But then if I point and can you give me that? Maybe what you're going to do is what you want is this, or what you want is this, right? So you, yeah, exactly. So you maybe, if I have this here, and then I point out, can I have that? What you're gonna do? Can I have that?
Yeah, what's that?
Exactly, you will say this or this maybe, right? So I'm gonna have feedback from you, right? So exactly, that's how we're gonna use this time to robot. So what I'm showing here is the same thing, but now with the robot. So I'm gonna just go directly to the example, maybe here. So here, Romeo was a postdoc in the lab. So he's just pointing to an object. He points to an object, the algorithm says, okay, the object maybe is going to be this sphere here, this puzzle sphere. So the robot goes there, but instead of actually catching the ball, look what the robot is doing. See? It's pointing down. So it's saying, okay, is this the object that you want? And then what he's going to do is say, with a gesture, can be changed for voice? No, that's not the object. So the robot immediately is going to try to search for the closest object and then point down to that one. So now again, is that the object that you want? And then he's going to say yes, another gesture, and then the robot is just going to finish the task. So it's just going to grasp the object. So here we were doing just like pick and place tasks. So he's going to grasp it, and then he's going to point where to put the object. So he just defined here one of these. Yeah, and I guess yeah, that's all. Almost in time.
Yeah, just one thing I want to point out is to just realize how inexpensive the solutions are using for this. They're just using a Kinect sensor. That's not the entire Xbox with everything, it's just the sensor and a simple laptop.
Yeah.
And it's just that, and see what they're able to do with that. So to me, that's what's amazing. They're not using sophisticated equipment or anything, just simple things available, and then use them totally with.
Cool. Thanks for coming out.
One last thing. I have to say that because I promised to say that. So we're doing, I guess you're all interested in robotics, right? At some degree. So we're actually building so all the software that I have done and we're working on is, we're building on top of ROS. I don't know if you're familiar with that. It stands for, can I use this? Robot Operating System. Well, actually it's not an operating system, but it's like a layer that you put on top of all your devices, and it's going to be really easy to communicate, for example, with an Arduino, with a Raspberry Pi, with any device that you have, and your computer, cameras, and it's just going to be really easy to integrate. So we're doing this group called ROS. So if you just Google this, ROS Edmonton.org, and if you want to give me your emails, I can send you an invitation. So we're going to start teaching how to